Hey ANPers, this is Dr. Jones checking in. This is ANP2 lecture test 4 video. I think we're on 8. 7's the last one I have written down. But we did that one. It was page 11, video 8. And this time we're going to start on page 12. Or if yours prints differently than mine, here. Respiratory performance and volume relationships. Dun dun dun. Okay, yeah, not like that. Not like that at all. Okay, so a spirometer is the machine contraption that measures volumes and capacities of the lungs. The pulmonary volumes are the tidal volume, which is this right here. Let's see if we can color code. Okay, tidal volume is from here to here. This is a normal inhale, normal exhale, one normal. How much air you move in a normal breath is your tidal volume. Resting tidal volume, roughly 500 milliliters. In the chart here, it shows the difference between the average male and female. When I give number ranges, most of them are the female average and the male average. And as always, these are only averages. They're obviously, while generally people with testes have larger rib cages and larger lung capacities than people with ovaries, it's not a hard and fast rule, just like men tend to be taller than women, but not always. Gwendolyn Christie towers over most of us. So again, just averages. Tidal volume, resting tidal volume is 500 mils. The expiratory reserve volume. So the expiratory reserve volume is when you inhale normally, exhale normally, and then exhale after a normal exhale. So the normal inhale and exhale is part of your tidal volume. So you're like, and then blow out all the rest of your breath. That's your expiratory reserve volume. It's a deep exhale after a normal exhale, 700 to 1,000 milliliters averages. The residual volume, okay, we're green now. Green, thanks. The residual volume is what's left in the lungs after an ERV. It's like there's always toothpaste left in the tube, there's always blood left in the heart, there's always oxygen, air left in the lungs. Not just oxygen, but air in general. Okay, so that is the residual volume. After you blow out the candles on the cake, you still have air. That's the residual volume. And that's 1,200 milliliters, and you need to add this minimal volume. When your lungs have collapsed, you still have air in your lungs. This is your minimal volume, 30 to 120 milliliters. The inspiratory reserve volume is after a normal inhale. Pooped, wait, we don't have a purple. Magenta. After a normal inhale, then you take as deep a breath as you can. So the normal inhale is still part of this tidal volume. Now it's supposed to be red. And then inhaling after that is your inspiratory reserve volume. And that is 1,900 to 3,300 milliliters. And feel free to pause this and go back through that. Capacities. The inspiratory capacity is the tidal volume plus the IRV. So the inspiratory capacity is you've done a normal exhale and now you take as deep an inhale as you can. That's your inspiratory capacity, and inspiration is in inhale. The functional residual capacity is the residual volume, the RV, plus the expiratory reserve volume. So after a normal breath, how much is left in the lungs? That's your functional residual capacity, plus E. So the RV plus the ERV. Okay. The vital capacity is what's, we gotta change colors. How much air can you breathe? Vital capacity from your biggest inhale to your biggest exhale. That's your vital capacity. So it's 3 volumes together. It's your inspiratory reserve volume plus your tidal volume plus your expiratory reserve volume. So from here to here. And then next is the total lung capacity, which is everything, 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 everything. So it's how much air is in your lungs at full capacity. Total lung capacity. Oh, I almost showed everything. Okay. Next. Okay, the actual process of gas exchange takes place between the air and the blood at the exchange surface, which is largely the alveoli, a little bit the respiratory bronchioles. Boyle's law, as a review, Boyle's law was that pressure, we're going white, okay, is inversely proportional to volume. So if you double the pressure, that halves the volume. If you have the volume, that doubles the pressure. If you double the volume, that halves the pressure. If you have the pressure, that doubles the volume. And I think I just said it all 4 different ways, but okay. So Boyle's law is pressure and volume are inversely related. Dalton's law. The major gases in our atmosphere are nitrogen is most of it, 78.6%. Oxygen, O2, and of course this is nitrogen into oxygen. Oh, that's why it's not showing up. It showed up top. How was the yellow show up? Sort of. So nitrogen is more than 3/4. 3/4 would be 75%. There's a little more than that, 78.6%. Oxygen is a little less than 1/4 at 20.9%, a little more than 1/5. Water vapor is 0.5%-ish. Carbon monoxide, 0.04%. Okay. So Dalton's law is that each gas adds to the total pressure in proportion to relative abundance. So if we had a second gas in here, but there were only 3 molecules, it would add a little pressure, but not a whole lot. If we had a third one in here, we'll make it green, and there were just boatloads of these green molecules, then they would add that much more pressure, because at this heat, they would be moving at a certain rate and they would bounce off the walls, creating pressure. And that's what gas pressure is. It's the pressure of these molecules hitting the walls of the container. And so the partial pressure is the pressure of each individual gas. And this is where the subscripts get wonky, because you've got capital P with a subscript N with a subscript 2. So it's the partial pressure of nitrogen. So it's P subscript N subscript 2. So we've got subscripts on our subscripts now. So if you add, so the partial pressure of nitrogen, since nitrogen is 78%, almost 80%, then that will be almost 80% of your pressure. Partial pressure of oxygen will be 20% because the composition of the air, oxygen, is 20.9%. The partial pressure of water is 0.5%. The partial pressure of carbon dioxide is 0.04%-ish. And these all add up to 1 ATM machine. No, 1 atmosphere. So that's Dalton's law, that each of the gases adds to the total pressure of the gas depending on its abundance, relative abundance. So if there's more of it, it's more of the gas pressure. If there's less of it, it's less of the gas pressure. Next page. So we talked about Boyle, B-O-Y-L-E. Boyle is gas pressure versus volume. Dalton is partial pressures. And now we talk about Henry. Henry's law. At a given temperature, the amount of gas in a solution is proportional to the partial pressure of that gas. Simple, right? Okay. So what this means, gases can dissolve into a liquid. And at a given temperature, the amount of gas in the liquid depends on the partial pressure of the gas in the air around it. So with a soda can, when you bottle them, you put under pressure, and that drives the air molecules, the molecules that were in the air, into solution. And then when you open that quickly, that the gas pressure decreases fast enough that it makes bubbles of the gas, and you get bubbles. So that's why you have soda bubbles. Henry's law, the soda bubble law. So at a given temperature, the amount of gas in solution is proportional to the partial pressure of that gas. So back on the note set, if the partial pressure goes up, if you have more gas in the air, then you will have more of that gas in solution in the liquid. If the partial pressure goes down, you will have less gas molecules in solution. The gas bubbles out of the liquid. And Henry's law to soda, when you open the can, you decrease the pressure quickly, decrease the amount of gas in solution, and it bubbles out. Solubility of gas, what does solubility have to do with it? If it is less soluble, there'll be less of it in solution. Like nitrogen, there's 78% of our air is nitrogen, and yet there's not a whole lot of nitrogen in our body fluids because it's just not that soluble in our body fluids. So that's why. Solubility. Less soluble, the less there will be in solution. How does Henry's law explain decompression sickness? Decompression sickness is the bends. And this happens when divers dive deep underwater and come up too quickly. So when you release this pressure gently and slowly over time, then the gas leaves solution, but not fast enough to make bubbles. When you release the pressure quickly is when it makes bubbles. So that's why if you open the bottle slowly, it won't bubble out and over. So in the bends, when you come up too quickly out of the deep, then the nitrogen gas that is in your body fluids, specifically the synovial fluids, make bubbles in the synovial fluid, and they hurt. And because those joints hurt, people tend to curl up in the fetal position, like curled up like a baby. And that's why it's called the bends. And the treatment for that is they put you in a decompression chamber, like a tube, a very tiny, like super claustrophobic looking tube. Yeah, there's a reason why I don't dive. Not on screen. And then they pressurize you and then very slowly over time release the pressure. So they pressurize you, and what that does is makes the gas bubbles, the nitrogen in the little gas bubbles, dissolve back into the fluid. And then they depressurize you slowly over time, and that allows you to come back to atmospheric pressure without making bubbles. So like a hyperbaric chamber for healing is a higher oxygen environment so that you could make more ATP to make more healing power. It's energy. It's used for cell division. Okay. And, diffusion of gases across the blood barrier. This feels like it ought to be a different video. Did I time this? Not even a little bit. Okay. Well, this feels like the place to stop, so we are going to. And we reviewed Boyle's law, covered Dalton's law, and covered Henry's law. So that's enough. Okay, now one more section. The alveolar air is different in that. The alveolar air is different than atmospheric air in that it has more carbon dioxide, less oxygen than atmospheric air. It is also warmer, more humid, and filtered. And that's mostly your nasal cavities, because the swirl of the air lets any particles in the air, dust or bugs or such, to get caught in the mucus that lines the nasal cavities. And so that and your nose hairs are the filters. And then the humidity, the warmth and the humidity are again because of the moisture in the mucus, that when dry, cold air, I know it's Texas, you don't know what I'm talking about, but it's a thing. When dry, cold air enters the nasal cavities with the swirling, it actually pulls the moisture out of your mucosa, out of that mucus, and into the air so that it's slightly less painful when it hits your lungs. And then as you exhale, if your mucus is dry, then that absorbs some of the humidity from your breath. And also if you're cold, it helps to warm it up. So it's an exchange. Okay, and gas exchange is efficient at the alveoli because, and we have bubbles. We have bullets. We're here. Efficiency. First bullet. There are big pressure differences. And bigger pressure differences make for faster diffusion. Always. Short distances, which we know makes for faster diffusion. The gases are lipid soluble. This means they can go through the cell membranes like they're not even there. And lots of surface area. That's what all those little alveoli are for. And the blood flow and airflow are coordinated, which is really cool, but unfortunately not something we're going to get into much. So the blood arriving, all right, we're going to finish the page. I thought we were done, but we're going to finish the page. So the blood arriving from the pulmonary arteries is low in oxygen, PO2, and high in partial pressure of carbon dioxide. How does the interaction with the alveolar air affect the arterial blood? Causes oxygen to enter the blood and carbon dioxide to leave the blood. So here's the alveolus, here's the alveolar air. We've got a PO2 of 100 and a PCO2 of 40. And then the pulmonary artery, which we know is blue, comes in with a PO2 of 40 and a PCO2 of 45. So because of the big difference between oxygen here and here, oxygen moves into the bloodstream from the alveoli, and the carbon dioxide, 45, is higher than 40, so it moves out of the bloodstream into the air for you to exhale, until the pulmonary veins and the alveolar pressures are equivalent or equalized. And the rapid exchange allows blood and alveolar air to reach equilibrium, which I just said. Okay, now we're going to call it a video. So this was video 8, Noteset pages 12 and 13. Did we do all of 12? Yeah, we started at the top. We did all of 12 and all of 13. Okay, 12 and 13. Thank you, as always, for tuning in. This no, I already did that part. Yeah, so the education must go on. The world needs healthcare workers now more than ever. Dr. J out. Maybe. Did it work? I hit Control Command Escape. It's not doing anything. Did I hit escape, or did I hit the question mark next to escape? Okay, let's try again. Control Command